Right, everyone. 11.7. This is the last section in chapter 11. All right. So in this one, we're going to talk about something that we later on are definitely going to take advantage of and use, right? But today I just kind of want to touch base and look at some of the basic ideas and basic how-tos before we have to apply this to something a little more involved. I don't know, not a great word for that. But anyway, cylindrical coordinates and spherical coordinates. So this is kind of like how you learned polar coordinates back in your pre-cal classes. Right, you're used to plotting and graphing and doing everything in rectangular coordinates, right? Your X's and your Y's, and now your Z's, right? But sometimes it's more helpful or easier for us to work with something that's written in a different coordinate system. So kind of like how in Calculus 2, you learn how to convert to polar coordinates so that you can integrate certain functions in a much easier way. Right here, we can learn how to convert both coordinates and equations between rectangular coordinates, cylindrical coordinates, and spherical coordinates. We'll start off with cylindrical. So think about what the shape of a cylinder is, right? It's a circular base and a straight edge going up and down, right? If we think about this translated to a coordinate system, it's kind of like if we have an XY plane and polar coordinates, and our Z-axis is the same, right? So think back to some definitions that you learned from polar coordinates. We know that in polar coordinates, x is r times cosine of theta and y is r sine of theta, right? And that kind of comes back from the idea that if you're on the unit circle, right, your x coordinate is equal to r times cosine of this angle, right? Similarly, your y coordinate is equal to sine, or your y coordinate is equal to r times sine of this angle, right? So those definitions do carry over into cylindrical coordinates. So x is r cosine theta, y is r sine theta. The z coordinate is unchanged, right? And again, that's because your xy plane, the floor, as we've been referring to it, is in polar coordinates, and your z-axis is still your z-axis. All right. And this is how we would convert from x's, y's, and z's into r's, thetas, and z's. If we want to go the other direction, um, so if I want to figure out r, theta, and z, right, I can remember some of the relationships that we talked about in earlier sections, right? Specifically that the radius r in polar coordinates is basically the magnitude of a two-dimensional vector. Pythagorean theorem. Right. We also know that theta, the angle that's made in polar coordinates, is the same thing as the direction of a two-dimensional vector that we talked about back in section 1, 11.1. Right. So that definition, both of those definitions carry over to this idea in cylindrical coordinates, right? So we can obtain r by finding the magnitude of the vector xy. We can find theta by doing arctangent of y over x. And then z is still z. There we go. So let's look at a couple examples that use these definitions. First, convert the point r theta z equals 4, 5 pi over 6, 3 to rectangular coordinates. So we know that r is equal to 4. That's the first number in a set of cylindrical coordinates. Theta is 5 pi over 6. That's the second number in a set of cylindrical coordinates. And we know that z is equal to 3. So z is not going to change. We already know the z coordinate. But to get r, oh, yeah. But to get x, we would need to find r cosine of theta. So here we know r is 4. We know theta is 5 pi over 6. And we know cosine of 5 pi over 6 is negative square root 3 over 2. All right, 4 divided by 2 would give me 2. So this is our x coordinate, negative 2 square root 3. The y coordinate we can get using our sine theta. So that's going to be 4 times sine of 5 pi over 6. 5 pi over 6, because we're in the second quadrant, we'll have a positive sine value. So this will be 4 multiplied by positive 1/2, also known as 2. So we got our x coordinate, we got our y coordinate, we already know the z coordinate. So our rectangular coordinate for this would be negative 2 root 3, 2, 3. And there we go. Next example, convert the rectangular coordinate 1 square root 3, 2 to cylindrical coordinates. So cylindrical coordinate means that we want to find r, theta, and z. So r we know is going to be the square root of x squared plus y squared. So 1 squared plus root 3 squared. Well, I know that this is going to work out to 4, right? 1 squared is 1, root 3 squared is 3. Add them together, you get 4, square root of 4, you get 2. So r is equal to 2. Next, we have theta. So we know that tangent of theta is equal to the square root of 3 over 1. So square root of 3. From our unit circle, that means that theta would have to be pi over 3, right? And think about why. If I were to rewrite this as unit circle coordinates, I could always write the square root of 3 as root 3 over 1. I could also write that fraction as root 3 over 2 divided by 1 over 2, right? The reason I do that is because now I can kind of see what the y coordinate is and what the x coordinate is. So we needed an angle where the y coordinate was root 3 over 2 and the x was 1/2. That would be pi over 3. So now that we have r and we have theta, remember we can just pull the z coordinate. My cylindrical coordinate would be 2 pi over 3, 2. And that's the cylindrical coordinate. Now, something that's definitely a lot more applicable to how we're going to use this later. Let's say we want to write an equation in cylindrical coordinates for surfaces represented by each of these. So first thing I notice, let's look at A. First thing I notice about equation A is the left-hand side is x squared plus y squared. If I go back to my definitions, that is what's underneath the square root here. So I know that x squared plus y squared altogether is the same as r squared. So I'm going to replace x squared plus y squared with r squared. And since z stays the same, we don't replace z with anything. Now we have an equation that's only in terms of r, theta, and z. Doesn't depend on theta, but that's besides the point. We don't have any x's and y's. We only have r's, thetas, and z's. Okay, now let's take a look at B. So for B, I notice that I have an x and a y, right? I don't have anything like this where I can directly relate it back to r, right? But I know that I can replace x and y individually using these two equations, which we also could have done in part A. We would have ended up with the same answer right after using a trig identity. But yeah, so if I replace y with r sine theta, and I replace x with r cosine theta, okay, we know that we'll basically get r squared sine squared theta is equal to r cosine theta. At this point, I do have an equation in terms of only cylindrical variables, so this is perfectly fine. Um, but just remember that this can be written in several different ways. For example, if I were to subtract r cosine theta from both sides, I could factor an r out. It would look different, but it would still be the same thing. If I were to, well, I wouldn't divide by r cosine theta because then you change the domain of the function, right? But um, there are a number of ways that you can rearrange a lot of these. The point, though, for this is to be able to get it to something that only involves r, theta, and z, right? And it could be missing one of those, but it doesn't involve x or y. Um, Next example, find an equation in rectangular coordinates, starting with the cylindrical equation. Okay, so first off, one thing I notice is that I have cosine of 2 theta. Yeah, there's not really a thing for me to use there that I can convert cosine of 2 theta to, but there's a trig identity that I can use so that it's on so that I can rewrite cosine of 2 theta as just something involving cosine of theta and maybe sine of theta, right? Specifically, there was a trig identity that you guys learned called the cosine double angle identity, which is something that you used a lot when you learned trig integrals in Cal 2, right? So remember, cosine of 2 theta can be written as cosine squared theta minus sine squared theta. That's an identity. That means that I can replace this with the other side of the equation, and it doesn't change this at all. In fact, what I get will be equivalent to what's currently there. So making that replacement, other thing, when you replace stuff, always remember to put parentheses around the new thing, because you never want to forget to distribute. Okay. All right. So keep in mind we're trying to get into rectangular form, which means that my final answer should only involve x, y, and z. Might be missing one or two of them, it doesn't matter, but I cannot have r's or thetas left over. So next thing I'm going to do is distribute the r squared. So we get r squared cosine squared theta minus r squared sine squared theta plus z squared plus 1 equals 0. So with this one, remember if I have something like this where it's r squared times cosine squared, I can write this as just r cosine theta, all of that squared. When we're multiplying, that's fine. When we're adding, that's not how that works because you have the middle term when you're adding. All right, with this one, I can do the same thing. So we have r sine theta, all of that squared. Okay, and r cosine theta, what's that? That's x. R sine theta, what's that? That's y. And now I have an equation that's written in rectangular form. Side note though, if you paid attention in the last video, you'll notice that this looks like it could be a quadric surface. So to be able to use the rectangular equation to maybe do something like draw a graph or explain the shape of a graph, right? You would want to rearrange this so that it's in standard form. Remember how that could work. You would subtract this 1 from both sides, and then you would need to divide by -1 so that the right-hand side is equal to 1. So we would end up getting negative x squared plus y squared minus z squared is equal to positive 1. That would be our standard form. And if I had to classify that quadric section, hopefully We enthusiastically said that it would be a hyperboloid of two sheets. Yep, that's what it would be. So all three terms are squared, two of the terms are negative, and we're equal to one. Yep, so that'd be a hyperboloid of two sheets. All right, now that we've talked about cylindrical coordinates, let's go to the other one, spherical coordinates. So spherical coordinates, also really useful, but you need to do a little bit of thinking to kind of understand how these conversion factors are accurate. So, first off, when we look at cylindrical coordinates, we go out a distance, we go around an angle, we go up an angle. I like to think of it as like one of those laser security systems that protects the priceless artifacts in museums. Yeah, it's like the laser beam shoots out and it scans around the room and it goes up and down. Yep. That's kind of like how spherical coordinates work, right? So you have three different coordinates when you're dealing with spherical. You have rho, which would be like the length of the laser beam. You have theta, that's the angle that it goes around on the floor. And then you have phi, or phi, people say it either way. I can't say phi because then I think of phi, phi, fo, fum. But anyway, that's going to be the angle that is made with the z-axis, right? So in this little paragraph, I actually say everything that I just said, what each thing represents, right? And you can tie it back to that laser security system analogy if that made sense to you. So to explain how these conversions work, right? The XY plane is still a polar coordinate plane, right? So those definitions that we talked about, x equals r cosine theta, y equals r sine theta, they still apply in the xy plane. But what you need to realize is that this r is not the same thing as rho, okay? So rho is actually the distance from the origin in three-dimensional space to the point in three-dimensional space. When the laser beam pops out, right, keep in mind the laser beam will grow longer as it goes up the wall, right? Because the distance from the beam to the wall directly is not the same as the distance from the beam to the wall at an angle, right? So rho is not the same as r, okay? But there is a relationship between them. So in that last paragraph, we know that rho is the distance from the origin to the point out in three-dimensional space. So this is rho. R is just the distance from the origin to the point that's right under that point. For these purposes, though, I'm actually going to draw that side up here, right? But it is going to be the same length. All right, so this is R, and then we have our Z coordinate right there. So the angle that is made with the positive z-axis, so z to rho, is our angle phi. All right. So to kind of understand where this rho sine phi comes from, let's think about what x and y actually are. So for x, we know that x is equal to r times cosine theta. To figure out r, we can use a little SOHCAHTOA to kind of form a relationship here. So r is opposite from phi. So if I look at sine of phi, that's going to be equal to r, the opposite side, over rho, the hypotenuse. If I rearrange this so that I can solve for r, I can multiply both sides of the equation by rho. So r is equal to rho sine of phi. Because of that, we know that x is equal to r cosine of theta. Well, we know what r is now in terms of just rho and phi. We know that, so we know that x will actually be defined as rho sine of phi cosine of theta. And that's where this comes from. Similar way with y, we know that y is equal to r sine of theta. since r is defined here, we can replace the r with rho sine of phi. So we have rho sine of phi, sine of theta. And that's where this comes from. So another thing I want you to be aware of, you might be looking at this and be thinking, oh, that looks a lot like the sine double angle identity. It's not. The reason it's not is because remember for all of your trig identities to work, the arguments, the angles that are being used in these trig functions have to be the same. That's phi, that's theta, they're not the same. So we could not use a double angle identity to rewrite that. For the same reason, we would not be able to write this as rho sine squared. It wouldn't work like that. Because again, this angle and this angle are not the same thing. So we have to just stick with it like this. And to take our conversions in the other direction, we can still use kind of these same ideas from what we learned about vectors. Except this time we don't have R being a magnitude for a two-dimensional vector. We have rho being the magnitude of a three-dimensional vector, right? Because remember, if we're in three-dimensional space, rho goes from the origin to the point, three-dimensional vector. Um, since theta is still only defined as the angle in a polar coordinate plane, right? We still have this exact same definition that carries over from cylindrical coordinates, right? You can still think of theta as the direction of a two-dimensional vector. With phi, though, you could you could actually get this conversion factor by just solving this equation for phi. If I divide both sides by rho and I replace rho with what it is in terms of x, y, and z, then I get this equation, cosine of phi is equal to that. So to get phi by itself, I would need to take arc cosine of the right-hand side. Okay, so with that, let's find an equation in spherical coordinates for the surface represented by each of these. Oh, that's supposed to be an equal sign. Yep, make sure you fix that on your notes. Um, all right. So anyway, we could start off by just replacing the x, the y, and the z with how they're defined up here. In the example with cylindrical coordinates, we were able to go with just replace that with r squared and bing, bang, boom. But that doesn't work here because r is not a part of spherical coordinates, right? So instead, we're just gonna replace x, y, and z individually. So x we're gonna replace with rho sine of phi cosine of theta. All right, don't forget your parentheses. Y we're going to replace with, I'll label this part. Y we're going to replace with rho sine of phi sine of theta. And Z we're going to replace with rho cosine of phi. So now, if I were to expand these, we'd get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equal to rho squared cosine squared phi. And if you look at your left-hand side, you can actually factor out rho squared sine squared phi. You're actually going to need to do that to see what's going to happen. So when I factor that out, I'm leaving behind a cosine squared theta plus sine squared theta. Since it doesn't matter what order I add in, I'm going to write it in this way so that perhaps you look at that and you scream immediately, that's one. Yep, that's one. That is indeed 1. Okay. So we can actually replace that entire thing with 1. And if I wanted to, I could also subtract rho squared cosine squared from both sides, or rho squared sine squared from both sides. Okay. And now you notice that you could factor out a rho squared from both sides. And if you remember the trick we used earlier, there's a trig identity that you could use here, right? Cosine squared of something minus sine squared of the same something can be rewritten as cosine of double that. So we can replace all of this with just cosine of 2 phi. And there we have the simplest possible form of that equation. Now, here's the thing. The important part is that you're able to make these replacements, right? And and get the equation so that it's only in terms of rho, phi, and theta. Technically, we did that at this step, right? But like on your homework, on the quizzes, maybe even on the test, you'll have questions where perhaps you're having to pick an answer choice that corresponds to one of these steps. And in that case, when you do have any kind of multiple choice question, um, you would need to stop wherever you match the multiple choice answer. If you don't have a multiple choice question, then it depends on what you want to do with that. Like if I wanted to take an integral, I wouldn't want to try to integrate that when I could just integrate this. That's way easier to integrate. So being able to simplify these things will make your life a lot easier when we're using this to take integrals, right? But with that said, go as far as you need to for the problems and for a little fun, see how simplified you can make the answer look, right? It's a good skill to have. Like I said, it's going to save you a lot of headaches down the road. So that's part A. Now we'll look at part B, right? So for part B, the first thing I notice in this equation is that the right hand or the left-hand side is x squared plus y squared plus z squared. That's what's under the square root for our definition of rho. So I could replace the entire left-hand side with just rho squared. And then with the right-hand side, we can replace the z with rho cosine of phi. And there I have my spherical equation. If I really wanted to, I could subtract this from both sides. I could factor out a rho, but there wouldn't be anything I could do with it at that point. So it's not particularly useful for me to do that. Other thing, I would not divide by rho, right? If you try to do that and say rho is equal to cosine of phi, you've actually changed the domain of this function. Because if you divide by rho, you would have to have a stipulation that rho could not be 0 since you can't divide by 0. Now, if you had something in the equation that already gave you that domain restriction, then it would be fine for you to divide by rho. But in this case, we're assuming that rho equals 0 is part of the domain. So we don't want to divide by rho because that would introduce a restriction, right? And with that, we have completed our lesson on spherical and cylindrical coordinates and thus have completed chapter 11. This definitely has the most parts out of all the stuff we're going to cover. Everything else I'm going to kind of condense into more compact things that make more sense. right? So with that, see you later. Happy mathing.